Good afternoon, everyone. I welcome you to the session on the Climate Science Special Report. We have a 2-hour session today. The first hour, or just less, will be a series of presentations presented here by our panel of authors from the report. So it's my pleasure to open this session on behalf of the authors. There's 3 coordinating lead authors. I'm one. Kathy Hibbard here to my right is from NASA, and Don Webbles from the University of Illinois, and 31 other authors, some of which are in the room and others on the panel. So CSSR, as we call it, is Volume 1 of the National Climate Assessment, the 4th National Climate Assessment. And it's a special item this time. It doesn't have quite a parallel it has a somewhat parallel in the past, but we've made it a more substantial part of the National Climate Assessment. In particular, it's longer, it's more in-depth, and it precedes the main part of the National Climate Assessment, which is Volume 2, led by David Reed-Miller, who's here. So there's a lot of distinguishing features of this report, and you'll see some today. 3 that I like to draw out is, number 1, National Climate Assessment is mandated by the U.S. Congress. So we as U.S. scientists are asked to do this, to report to the government and the people of the United States what exactly is the deal with future climate in the United States. And so in that sense, we have a special mandate and a special responsibility to do that. And secondly is how this document has been reviewed. Because it comes from within the government, it's approved by the government. And this particular report was approved by the White House and by 13 agencies of the federal government that are part of the U.S. Global Change Research Program. And so this really is a very distinguishing feature. In addition, the report was reviewed 7 times over 2 years, which may put it in a very unique category. And then the final point I draw out is it has a really, what I would say is an outstanding executive summary to this 500-page report. And as the author team spent a lot of time making this summary of value to the non-specialist, essentially to the U.S. public as well as scientists. And I urge everyone here to get a copy of it. There's actually 100 or so copies at the back of the room. That young lady holding a copy up will distribute those till they run out. And other than that, you can go to booth number 745 in the exhibit hall from the USGCRP program, and they have another stack. So before we get started here, I'd like to introduce Mike Kuperberg, who's the Executive Director of the U.S. Global Change Research Program. A report like this is a very complicated business, and USGCRP, from an author point of view, did an outstanding job of shepherding this through the process that spanned 2 administrations. So Mike will say a few words to this group before we get started. Mike?
Good morning, afternoon already. Thank you, Dave. My name is Mike Kuperberg. I'm the Executive Director of the U.S. Global Change Research Program, and what I'd like to do in 2 minutes or less is orient you to USGCRP, explain to you what this report is and how excited we are to have been able to complete and release it. USGCRP was created by a law passed by Congress in 1990, the Global Change Research Act. That law essentially tells the USGCRP that we have to do 3 things. We have to coordinate science across the 13 federal agencies that are named in the Act. We have to produce a series of mandated products, the National Climate Assessment being one of those, and we have to work to inform decisions or to assist the nation in responding to global change processes. We do that through a number of processes, and I'd love to catch one of those of us with USGCRP name badges. We'd love to talk to you about the program. But today, the Climate Science Special Report, as Dave said, Volume 1 of the National Climate Assessment is a critical piece we have out. I commend it to you. I also commend to you the 2nd volume, NCA, the Impacts Assessment, the 2nd volume of the National Climate Assessment, which is currently out for public comment. If you go to reviews.globalchange.gov, you'll find access to that draft document, and we encourage you and solicit your review of parts of that document, all of it if you're so inclined, and to please provide back to us your thoughts and input. It's that kind of thorough, rigorous review that led to the high-quality product we have with the Climate Science Special Report and will lead to the high-quality product that we expect to release in December of 2018, the second volume, the Impact Assessment. So with that, let me end by saying thank you. Thank you to the 3 convening lead authors here. Thank you to the 31 lead authors. Thank you to the review editors who worked so hard on this. Thank you to the staff within USGCRP who led and made this report happen. And thank you to the community that provides the input, the technical expertise, and the information that we use to make this report happen. With that, thanks a lot, and let me turn that back to Dave.
Thank you, Mike. So our program today will start with a long introduction from Don Webbles of the University of Illinois, who will basically give us an overview of the Climate Science Special Report. And that'll be followed by 5 shorter presentations from authors who will represent parts of the 15-chapter volume. And we hope to get that done within an hour or so, and then open the floor to questions to the panel, which will stay at the front of the room. So thank you. Don, please start.
Thank you. We got it out. We were a little shocked, but yes. So what I'm going to do is give you a quick overview of some of the findings, and then my colleagues will expand upon that, and then we can talk about it all together with you all after our talks. So first of all, go to the web and get the report. If you want you can pick up here the executive summary. There are printed versions of those. I think they're available right in the back from some of our friends at USGCRP. I have a couple of myself, so if they run out, I have some. Or you can go to the booth for USGCRP, which I think is 745 in the exhibit hall. So we'll talk a little bit more later about the second volume, but first let me go through what we're doing here. Oops, what's going on? It's not moving. How do I move slides? Yeah.
Escape.
Escape.
Escape
Here, let's see if that does it. No? Is that the wrong one? Oh, okay. There we go.
All right, there we go.
What do I need to do?
I just clicked it.
Just click it?
Yeah, and then click to the right for the next one, right?
Okay, so I can't use the arrows here?
I would just use the mouse.
Okay, sounds good.
Great.
Okay. So, as you've heard already, this is a comprehensive assessment of our understanding of how the climate is changing and how it's affecting the weather across the United States. The focus is particularly on the United States, but the first few chapters do give kind of an update on global understanding as well. It is written largely for the technical, technical aware, but the executive summary is written more for the public. And so we took out some of the jargon there and tried to make it more understandable. And it provides a foundation for the second volume, and which focuses more on the impacts, as Mike mentioned. Okay, why is this? There we go. Is that it? Oops. There we go. Very touchy. Since the third climate assessment, there have been many new observations, lots of new published research that have increased our understanding of what is happening to our climate system, both in the past, current, and future time periods. And we also have stronger evidence for the continued rapid human-caused warming of the planet and how we can, the analysis that lead us to make that conclusion. We also have had significant advances in understanding extreme weather events and how they are related to the changes occurring in climate and that relationship to human events. So the bottom line from the assessment, just to summarize it in one page, is our climate is changing. It's changing now. It's not sometime in the future. It's happening right now. It's happening extremely rapidly. Severe weather is becoming more intense, particularly certain types. Sea levels are rising. It's largely happening because of human activities and associated pollution, particularly the emissions of carbon dioxide and other gases from human activities. And the climate will continue to change over the coming decades and potentially centuries. There are many indicators of the changes occurring in climate. It's not just the increases in temperature on land, ocean, and atmosphere, but also what's happening to glaciers around the world, Arctic sea ice extent, snow cover, Pacific humidity, the fact that a warmer atmosphere should hold more water vapor is seen very well in the observations. The ocean heat content, over 90% of the energy that is being produced from those increase in greenhouse gases and the effect they have on radiative forcing on climate is ending up in the oceans. And so we're not seeing nearly as much climate change as we might have if that weren't occurring. And we're seeing, many, many others. There's many other indicators besides these. If we look at the global temperature, since 1901 to 2016, we've seen an increase of about 1.8 degrees Fahrenheit, 1 degree Celsius in temperature, with the largest changes having occurred since the 1960s. If we looked at every decade, so do this a decadal analysis, we see the last 5 decades has been warmer than the other, and I think if we were to continue this, we will see that the next decade will be warmer still. This period is very unusual in human experience, such that if we put the current temperature record on top of the paleoanalysis of the temperatures over the northern hemisphere over the last 2,000 years, we see that the current temperatures are very unusual, extremely much higher. And yet you can see the medieval warm period in the temperature record, and you can see the Little Ice Age in the temperature record. But now we're much higher than those types of temperatures. Looking at the planet as a whole, I've already mentioned that the recent temperatures have been extremely high. Since the last assessment, in fact, 2014 was then the warmest year on record, followed by 2015 became the warmest year on record by a small amount. And then, and that far surpassed, 2014. And then 2016 was warmer yet. 2017 is likely going to end up second or third warmest, based on the last analysis I've seen. 16 of the last 17 years are the warmest years on record for the planet. Then if we look at the distribution of temperature across the planet, this is relative to the period 1901 to 1960, and the reason we did that is explained in the report, is because we wanted to account for in the United States, not globally, in the United States, the 1930s were particularly a warm period, and so we wanted to include that in our baseline. When we do that, you see that where we have observations, and we don't have observations over this entire period on the poles particularly, which is why they're gray there, but almost all areas of the globe, particularly over land masses, have seen a significant increase in temperature. There are 2 exceptions. One is off the coast of Greenland, where the melting ice is producing more fresh water, both from land ice and sea ice. That is having an effect on ocean circulations based on latest analysis. And then the other is in the southeast United States, where it may be perhaps because of circulation changes, but also because of deforestation in the 19th century, followed by forestation in the 20th century, may have an influence there. And we'll see that on the next slide, which shows the temperature over the United States. Very similar to the global change from 1901 to currently, we have seen about a change of about 1.8 degrees Fahrenheit over the U.S., and many areas of the United States have seen a very extensive warming, except for a few areas in the southeast, as I mentioned before. Much of that change has occurred in the winter, less so in the summer, in part related to changes in precipitation patterns as well, but generally that is what is found. Precipitation generally has increased, particularly over the central part of the United States and the Northeast, while some other areas have dried, particularly the Southeast and Southwest, with much of that change occurring in the spring and fall seasons. Now, we're going to have a little talk about Alaska and the polar regions later, but I'm just going to give one slide that shows that the residents of Alaska, residents actually of the Arctic, are on the front lines of climate change. They're seeing much more rapid changes than we're seeing here at mid-latitudes. And those stark examples of those kind of rapid changes include the accelerated melting of the sea ice cover, where we've seen very significant losses in sea ice cover over the last 30, 40 years. Mass loss from the Greenland ice sheet and other ice sheets in the Arctic, and reduced snow cover, and finally permafrost melting, which is of concerns for a number of reasons, including the potential for increasing the amount of emissions of carbon dioxide and methane over this century. One of the biggest issues for climate change is not just the changes in temperature that are occurring, but what's happening to extreme events. We're seeing more an increase in the number and intensity of a number of extreme events. One way we can tell this is by looking at the analysis that NOAA has done starting in 1980, where they look at the billion-dollar events, and where there used to be a couple events per year early in that time period in the 1980s. We're now seeing typically over 10 such events every year, and in fact this year we're probably through September we had 15 such events, and I think we've had 2 major wildfires since then. That probably has raised it to at least 17, and there may be some other events I'm leaving out. So what is very unusual is becoming quite usual. These analyses do account for inflation, and so they're trying to put them on the same scale, and they've affected all parts of the United States. In all, the American people are being affected to the tune of $1.1 trillion over this 37-year time period. The similar analysis has been done worldwide, but I'm not showing those here. So, as I mentioned earlier, we're seeing more extreme temperature events, more extreme precipitation events. Generally, heat waves are generally increasing in number and intensity in the U.S., particularly since the 1960s, worldwide over the entire century plus. And cold waves are decreasing both in the U.S. and worldwide. More precipitation is coming as larger events. When we're likely to get either rainfall or snowfall, it's more likely to be a large event compared to the past. That's resulting in some areas having more risk of floods, particularly in the analyses in the Northeast and Midwest. But we're also seeing some regions, as I showed earlier, becoming drier, so we're seeing more likelihood of droughts in some regions, particularly in the Southwest and Southeast. Incidence of large wildfires has increased, particularly in the western United States and Alaska. We've seen an increasing intensity of Atlantic hurricanes. Tornado activities are more variable. We have seen an increase in outbreaks, but we can't tell much about intensity at this point. And hail may be becoming more intense based on some new analyses, but also remains highly uncertain. All of these trends, though, are likely to continue, and we'll talk a little bit more about that. The frequency of extreme heat events are increasing in most continental regions of the world, including the United States. The graph on the right shows the changes in record highs in red versus the changes in record lows. And generally, the record lows are decreasing in number, and the number of record highs are increasing in number. Looking at extreme precip, just one example, there's many others in the report. We've generally seen an increase throughout the United States and again worldwide in the number of extreme precip. This by decade. In the first case, over the U.S. in terms of 2-day precipitation events exceeding 5-year reoccurrence. And then on the right shows the 99th percentile precipitation from 1958 to 2016. This is following an analysis that was used both in the 2009 and the 2013 assessments and kind of updating that. And like those assessments, shows that the largest increases have been in the Midwest and the Northeast. I've already mentioned the increasing trends in wildfires, and certainly that's been a very, very major problem this year. And the 9.2 million acres was as of 2 months ago, so it's probably way under, or as about a month ago actually. It's way underestimated based on what's happened recently. But the fire season is generally about 3 months longer than it had been 40 years ago. Fires are tending to be hotter because of the dryness of the material, and they're spreading faster and presenting far greater risk. In Alaska, even the tundra has been experiencing wildfires. There are many lines of evidence demonstrating that human activities, especially emissions of greenhouse gases, are primarily responsible for the observed climate change. For the period extending over the last 50 years, there are no credible alternative explanations supported by the extent of the observational evidence. It's not the sun. Solar output changes and natural variability can only contribute marginally to the observed changes in climate over this time period. There are no natural cycles found in the observational record that can explain the observed changes in climate. There are many, many different types of analysis that lead to these conclusions about human activities. I won't be able to show you very much here. There is one example, though, where in the report, we look at the period from 1750 and look at the forcings on climate. We actually have several different types of examples in the report, but this one looks at the contributions to the rate of forcing on climate since 1750, and we've had very little effect from volcanic eruptions, which tend to cool the atmosphere for a few years, or from solar radiation, but a huge input from the changes in carbon dioxide, methane, nitrous oxide, and other gases and particles that are affecting the Earth's climate system. The current concentration of carbon dioxide is about 405 parts per million. That's far above the long-term record, at least over the last 800,000 years using ice core analysis, but we can go back further than that and show the last time that we've seen such levels was about 3 million years ago, and a much, much warmer Earth than we have previously, than we have currently. The climate will continue to change, and as in IPCC and the third National Climate Assessment, we look at scenarios for future emissions of those gases and particles that I mentioned, using the RCP scenarios that were analyzed by a number of different climate models around the world for the fifth IPCC assessment. And generally, those show that the pathway we're on now, which is to follow the high emissions, would lead to the order of 8 to 10 degree Fahrenheit increase in temperature by the end of the century. Hopefully, we can reduce that significantly over the coming decades. To get to 2 degrees, though, will be much more difficult. I'll talk a little bit more about that later. Oops, wrong way. Looking at the projections over the coming decades, over the next few decades, there's little difference between those different scenarios because the emissions we've already made to the atmosphere are largely affecting the changes we'll see over this time period. And so we're already kind of committed to a certain level of climate change over those decades. But by the middle of the century, and certainly by the end of the century, you see significant differences between the emissions and their resulting effects on climate. And that tells us that how much emissions we make really can make a huge difference in what climate change we see in the long term. In the United States, looking at extreme weather again, the projections suggest that we will, this is from a downscaled product that we did for the assessment that shows a number of days above 90 degrees by mid-century relative to now. That basically shows a significant increase throughout the country in terms of the number of days, increasing the number of days above 90 degrees by over a month in many, many cases. But likewise, the number of days below 32 degrees is likely to decrease throughout the country, again, by a significant amount. We're likely to see more extreme precipitation in the coming decades, particularly for the high and intermediate scenarios. More likely to see more intense hurricanes, as we already discussed, but not necessarily in the number of total hurricanes, but in tropical cyclones. And also, if we look at the sea level rise in combination with the increase in frequency of such events, the extent of extreme flooding associated with coastal storms is likely to increase. Generally, sea level rise is now the highest rate in at least 2,800 years, from our chapter on sea level rise. The chapter after that looks at acidification, the increase in acidification of the oceans. The oceans becoming less basic, and it's likely to continue throughout the century as we increase the amount of carbon dioxide, and about 25% of that carbon dioxide ends up in the oceans where it turns into carbonyl acid. Changes are also occurring in the ocean circulation and in the oxygen levels in the ocean that also are of concern. One of the things we're already seeing is a significant increase in the amount of nuisance flooding. When there's a high tide, there's more likely to be an increase in floods in streets in a number of cities throughout the United States. And as we look at projections for that over the coming decades, that's only going to increase as an issue to the point where some places may become unlivable as a result. Looking at I'm going to skip over the top of this, which is mostly focusing on the rate of change, but looking at the bottom, projections suggest, much like we produced for the third National Climate Assessment, most likely changes are an increase in sea level rise of about 1 to 4 feet over this century. But what's different for this assessment is because of the uncertainty particularly in what's happening to the Western Antarctic ice sheet, we can't say for sure that it couldn't be as high as 8 feet. The U.S., particularly the eastern part of the U.S., eastern half of the U.S., is likely to see more than that because of subsidence and other aspects of the forcing affecting sea level rise in those areas. So instead of seeing on the order of a meter, 3.3 feet, many regions in the U.S. might, if that were to be what's happening worldwide, they might see as much as 5 or even 6 feet in some areas. And that would be a very significant concern. I mentioned the issues about trying to stay at 2 degrees or less relative to pre-industrial levels. Chapter 14, which Ben's going to talk about in a little bit, looks at other future scenarios and what mitigation could mean relative to those. Basically, the cumulative global carbon dioxide emissions must stay below about 800 gigatons of carbon for a 2/3 chance of preventing 2 degrees centigrade. We can likely, following the pathways we're going now, somewhere between an RCP 8.5, the high scenario, an RCP 4.5, kind of a lower scenario, we got about 20 years before we're likely to reach that. So what's going to happen in terms of choices that are made in the future really could make a big difference in this, and but nonetheless, we may have to reach the point where we actually have to remove carbon from the atmosphere if we're going to stay below 2 degrees. Another big aspect in the report is Chapter 15, which looks at potential surprises. There's a significant possibility for unanticipated changes in the climate system. If anything, the models are probably tending to, an average model is tending to underestimate the changes that are occurring. Two things we really discuss in this chapter in more depth is the possibility of tipping points and also compound extremes, where you have heat wave and droughts combined, for example, and the potential impacts of that on human systems could be very significant. Basically, the further the Earth system departs from historical climate forcings and the more the climate changes, the greater the potential for surprises. And such changes are possible throughout this century. I'm going to finish by recommending that you take a look at Volume 2. As Mike mentioned, you can sign up to review Volume 2 and its look at the impacts and risk and adaptation for the United States. And you go to review.globalchange.gov to do that. And thank you.
Thanks, Don. Next, we'd like to bring up Patrick Taylor from Langley, and he's going to be talking about Arctic changes and their effect on Alaska and the rest of the United States. These will be short talks just to review some of the major themes and chapters of the Climate Science Special Report, followed by any questions from you guys to the panel.
It's increased a lot.
Do you? Oh, yeah.
Thank you. So the Arctic climate system is changing fast. That's kind of the bottom line. It's been about 40 years since Manabe and Weatherall's projections suggested that the Arctic would warm faster than the rest of the planet to increase CO2. And the recent observed and in several cases unprecedented changes that we've seen in the Arctic climate serve to verify this prediction. These changes include the increase in click the slide. Aha. These changes include the fact that the Arctic is warming twice as fast as the rest of the planet. And the significant declines that Don showed in sea ice extent and in volume. Also, the observations show a much longer sea ice melt season, where in particular in particularly in coastal Alaska, we've seen that the length of the melt season has increased by more than 60 days in some places. Rising permafrost temperatures and continued thaw have spurred additional CO2 and methane release. So this permafrost carbon feedback, while uncertain, has the potential to compromise our ability to limit any global temperature increases. Additionally, reduced snow cover and mass loss from Alaskan mountain glaciers and Greenland have also been observed in this time. According to NASA's GRACE mission, the average annual mass loss from Greenland between April 2002 and April 2016 was 269 gigatons per year. That's enough water to fill about 130 million Olympic-sized swimming pools. All signs indicate that the magnitude and pace of these changes will continue. For instance, the report documents that sea ice-free summers over the Arctic Ocean are likely by mid-century. Let's see. We'll leave it here. It's supposed to animate, but that's okay. That we'll see sea ice-free summers by mid-century. This puts us on a path that's been unobserved in about 2 million years. While there exists large uncertainty in exactly how much the Arctic will change going forward, anecdotally, over the year and a half or so we were writing this report, I noticed that each new research paper that tended to come out during the time tended to suggest the larger changes were more likely than the smaller changes. Human activities are also impacting the Arctic. And our findings here ratchet up some of the likelihood and confidence statements that came out of the last IPCC report on the anthropogenic fingerprint of climate change in the Arctic. It's very likely that human activities have played a role in Arctic climate change. We justify this based on the number of new studies that came out and as well as the emerging science of extreme event attribution, which in particular argued that the record sea ice extent minimum in 2012 could not have happened in the absence of a human influence. Now, the U.S. is an Arctic nation. It's an often overlooked fact. Therefore, the decisions that the United States makes about adaptation, mitigation, resource development, trade, national security, economics, transportation, etc., all depend on projections and on information about Arctic and Alaskan climate change. However, these observed changes and the projected ones in the Arctic affect more than just the people that live in the Arctic, but have consequential impacts for human and natural systems globally. What happens in the Arctic doesn't stay in the Arctic. I use this phrase not motivated by the controversial but potential links between Arctic climate change and the extreme events in mid-latitudes, but rather because the influence of Arctic climate change, the influence that Arctic climate change is having on the global energy budget, global sea level, and the carbon cycle. This is an important takeaway message for me in particular, because while this may be obvious to us as scientists, it's a question I hear frequently when doing public speaking is, why do I care about the Arctic? It's so far away, it doesn't affect me. And so clearly, like throwing a rock in a pond, these changes in the Arctic are having ripple effects with a global reach. The Arctic is a unique region. The inaccessibility of the Arctic has made it difficult to sustain the high-quality observations of the atmosphere, ocean, sea ice, and of the entire system that are required to improve our physically based models. The improved data quality and the increased spatial coverage will certainly enable us to address societally relevant science questions going forward. But despite these challenges, our scientific knowledge is sufficiently advanced in order to effectively inform policy, and that's discussed in the chapter. The significant scientific progress and the knowledge about how the Alaskan and Arctic climate will change, has changed and will continue to change is documented in the chapter. So in closing, while the findings of some of these key findings that I scrolled up here while I was speaking may not be completely new, in many cases we've been able to strengthen our confidence in likelihood statements relative to the previous assessments. We've seen a lot of changes in the Arctic over the last 30 years, and these changes will continue. All signs indicate that the biggest and fastest changes in the Arctic may lie ahead. Thanks.
Thanks, Patrick. Next, we're going to have Dave Easterling, who will be talking about observed and projected changes in climate extremes in the United States.
Great, thanks. So what I'm going to talk a little bit about is observed and projected changes in extremes, and this is sort of a combination from two chapters. Chapter 6, which is on temperature changes. Russ Vos was the lead on that one, and I was the lead on Chapter 7, which is precipitation changes. And then Ken Kunkel was my sort of co-lead and did a lot of the heavy lifting in Chapter 7. Don showed this map, and just keep this one in mind. You have annual temperature, and so this is annual average temperature. The way we take, climatologically, the way we take temperature measurements, we have a daytime high and a nighttime low, which is what we actually use to analyze temperature extremes. But you can see that in much of the warming was in the winter, as Don said, less so in the summertime. We actually have some areas that cooled. So kind of keep these in mind when we look at a little bit of the extremes. Okay, this is observed changes in heat and cold waves, 1901 to 2016. So on the top is the change in cold waves. These are 3-day duration cold waves where the temperature goes below the 10th percentile, the minimum temperature, so that's the the nighttime low. And you can see that we have a fairly steady decline in the number of cold waves starting in about 1901. You don't really see the impact of the 1930s all that much there, the droughts and the warm periods of the 1930s. Where you see the impact is actually in the lower left, which is the number of warm spells. You can see you have a big spike in the 1930s, then a decline to about 1970, and then we begin increasing in the number of warm spells. So you're seeing much more of the impact in the cold temperatures in terms of the overall warming. And we have this, you can see the 1930s are still kind of the period of record in terms of these warm spells. And you can see again in the intensity, the magnitude of the heat waves is the bottom right graph. You can see again, you have that big spike in the 1930s, but again, it's beginning to gradually increase again. These are projected changes. Don showed changes in number of days above 90 and number of days that go below freezing, so we have a decline in the number of frost days into the future. We've seen that in the observed record. We also expect to see the number of days over 90, as well as these are the warmest temperatures of the year in the upper right. So in the upper right is the average, the model average. And we have the projected change in the coldest temperature year in on the left side, sort of the left column, and the right column is the warmest day of the year. And we showed two of them in here because we have the mean of the three warmest models, and that kind of gets into the sort of the risk-based framing that is going into the volume 2 of the fourth National Climate Assessment. We begin looking at the impacts. As you can see, all of them show very distinct warming. If we look at changes in heavy precipitation, again, many of you are familiar with these maps. The upper right is the one that Don showed, changes in the 99th percentile from 1958 to 2016. That's been updated a number of times. It's actually appeared in a number of the assessments. But if you look at the left, you can see we begin taking a longer term view of it from 1901 to 2016, and you see similar patterns. You see the very large increases in the number of heavy precipitation events. If we look at the projected changes, these are projected changes in the 20-year return period. Again, we have the lower emission scenario on the top, so this would be RCP 4.5. And 8.5 is on the bottom. The left side is what happens in the mid-century, right around 2050, and the right side is what happens at the end of the 21st century. You can see in all cases you see increases, and you see very large increases in late century and the higher emissions, especially in the lower right map. You see very large increases in heavy precipitation events. Okay, and this is my last figure, and this is actually an interesting figure because very often you hear that the projected increases in heavy precipitation events occur at the expense of lighter events. Okay, and so that's exactly what this is showing. These are number of events by percentile bends. You can see the largest increases are at the very end of the ones that are above the 95th percentile. These are the difference between model projections at the end of the 21st century and the end of the 20th century. So you see what you always hear, that you expect to see more of the increases at the expense of the lighter events, and this is exactly what this figure shows. I think that's it.
Thanks, Dave. Next, we're going to have Robert Kopp talking about rising seas and changing oceans.
So I'm going to cover some of the findings of the reports with respect to sea level and changes in the ocean, drawing primarily upon Chapter 12 of the report, which I worked on together with several people and was led by Billy Sweet, and to some extent also on Chapters 13 on ocean acidification and other biogeochemical changes, and Chapter 15 on potential surprises. Just use the... Okay, great. So global average sea level, as Don mentioned, has risen by about 16 to 21 centimeters since 1900, as you can see in the 4 reconstructions shown here, which are based on tide gauges. And about 7 centimeters of those changes have occurred since 1993, a rise seen both in satellite and tide gauge-based records. One of the drivers of this rise has been changes in the cryosphere. Another driver has been changes in the heat content of the ocean, which can be seen in this figure, showing ocean heat content at 0 to 700 meters, 700 to 2,000 meters, and 0 to 2 kilometers, has increased at all depths since the 1960s. This increase in ocean heat content has also been reflected in sea surface temperatures, as shown here in 3 data sets going back to the late 19th century, which show an average rate of rise from 1900 of about 0.7 degrees Celsius per century. Don mentioned the role of attribution studies in this report, and there has been some attribution work on sea level rise. And although quantitative attribution studies give a range of estimates of the proportion of sea level rise attributable to human-caused warming, all indicate that human activity contributed substantially to the rate of rise seen since 1900. This particular figure is showing you one estimate of this, with the red curve being a model projection of sea level rise in the 20th century under observed temperatures, and the blue curve in the absence of 20th century warming. So from this study, roughly half of the 20th century change is attributable to the 20th century warming. And as Don mentioned, the rate of rise since 1900 is faster than during any preceding century in at least 2,800 years, as can be seen in this geologically based reconstruction of sea level rise over the last 2,500 years. This report introduced new sea level rise scenarios, building upon the ones that were developed in 2012 for the third National Climate Assessment. In these scenarios, there are 6 of them that range from 30 centimeters of sea level rise in 2100 at the bottom to 250 centimeters at the top. The lower bound, the 30 centimeter numbers, is higher than the value used for the third National Climate Assessment, and it's based on an extrapolation of the linear trend over the last couple decades. The elevation of the upper bound, 250 centimeters, is based on several lines of reasoning, including literature estimates of maximum physically plausible values, observations including the onset of marine ice sheet instability in parts of Antarctica, and new modeling regarding the importance of marine ice cliff instability. The CSSR also, for the first time, uses the literature on probabilistic projections of sea level rise to contextualize these scenarios. That's what those bars on the right are sort of indicating, the thick bars being 90% probability intervals from a range of probabilistic studies, the thin lines being the potential extension of those based on new findings regarding Antarctic ice sheet instability. The study finds that it's very likely that there will be between about half a foot and 1.2 feet of global average sea level rise in the first half of the century, and it's very likely that there will be between 1 and 4 feet over the course of the century, but that Antarctic instability could make higher numbers plausible. The new scenarios also, for the first time, include fully localized projections of sea level rise, as shown here for the intermediate to 1 meter scenario. And the rate of local sea level rise they find is likely to be greater than global mean sea level rise in the U.S. Northeast and the western Gulf of Mexico in all scenarios, and in high scenarios likely to be greater along almost all U.S. coastlines. And Don mentioned that minor tidal flooding has already increased 5 to 10-fold in several U.S. coastal cities due to the observed sea level rise, that's shown here in the orange, and is projected to continue to increase substantially. A majority of tide gauge sites will, by 2040, experience the historical 5-year coastal flood about 5 times a year, a 25-fold increase in amplitude. This figure is showing you the timing of when that 25-fold increase occurs. Now, sea level rise is not the only change going on in the ocean. Oceanic CO2 absorption is leading to a decrease in ocean pH, shown in the green and the black there on the bottom, at a rate that may be unparalleled in the last 66 million years. And as discussed in the potential surprises chapters, potential feedbacks have the potential to shift the Earth's climate system into new states. For example, one in which Greenland or Antarctica are significantly deglaciated, consistent with the higher extreme scenarios, or one in which the Atlantic meridional overturning circulation is greatly reduced. Although a complete collapse of AMOC is unlikely in this century, a significant slowdown in the range of 10 to 50% is possible under a high emission scenario and would have an impact both on ocean heat absorption and carbon absorption and on sea level rise on the northeastern U.S.
Thanks, Robert. Next, we're going to have Michael Weiner talking about detection and attribution.
On the Mac. Good afternoon. I'm Michael Weiner. I'm a senior scientist at the Lawrence Berkeley National Lab and a member of the lead author team for this report. I'm also the current chair of the International Detection and Attribution Group, a long-standing ad hoc group of scientists interested in understanding the human role in observed climate change. I must point out, according to the terms of the Department of Energy's policy on scientific integrity shown on this slide, that the views I state today are not necessarily reflective of the United States Department of Energy, the Lawrence Berkeley National Laboratory, the University of California, or even the other members of the team. These views are my own and not intended to reflect any U.S. government policies or positions. Thank you. Formal detection and attribution studies are assessed throughout this report, particularly in chapters 6, 7, and 8. New developments in the science of extreme event attribution are reported for 30 different events within the United States, including heat waves, cold snaps, wet seasons, individual storms, and droughts. Most, but not all of these events revealed an influence from the human interference in the climate system. It is no longer appropriate to state that the influence of anthropogenic climate change on specific individual weather events cannot be quantified. Rather, very much can be stated, sometimes with high confidence, on the effect of global warming on highly impactful weather events within the United States and elsewhere. In the aftermath of this past year's heat waves and hurricanes, this attribution of the effect of human activities on individual extreme weather events is even more important and interesting. As you can see, the report finds that there is a significant human influence on nearly all recent heat waves and cold snaps. Analyses of the human influence on heavy precipitation seasons, as well as individual extreme storms, were assessed. Analysis of high-impact storms presents numerous special challenges, and the field is rapidly evolving. I would note there are at least 2 attribution papers on Hurricane Harvey's unprecedented precipitation published since this assessments report release that are being presented at this AGU meeting, which is why I'm running down to the poster sessions immediately afterwards. Next slide. Attribution statements for meteorological drought are decidedly mixed, including that recently experienced in California. The human effect on agricultural drought, a soil moisture deficit, is somewhat more straightforward, at least at the surface, due to the strong relationship between increased evapotranspiration and warmer temperatures. I would like to turn now to the more traditional detection and attribution results assessed in this report. Much attention has been paid in the press to the statement in the executive summary, quote, "It is extremely likely that human activities, especially emissions of greenhouse gases, are the dominant cause of the observed warming since the mid-20th century," end of quote. This statement in the executive summary is based on key finding number 1 from chapter 3, and I quote, "It is extremely likely that more than half of the global mean temperature increase since 1951 was caused by human influence on the climate," end of quote. In fact, this is the most conservative statement that could be made about the human influence on the observed climate. The phrase extremely likely is taken from the calibrated language of the Intergovernmental Panel on Climate Change and has special meaning. In this statement, it specifically refers to the result that the lower bound on a 5 to 95% statistical confidence interval of the human contribution to the observed increase in global mean surface air temperature is estimated to be greater than 1/2. The specifics of this confidence interval are based on climate model simulations. However, the statement is consistent with other techniques that don't use models to estimate the human increase in surface energy budget. Some of these techniques date back to the 19th century. The report goes on further to make a statement not just about the lower bound of the human influence on the climate system, but to make a best estimate of this influence. Also from key finding number 1 of chapter 3, and I quote, "The likely range of the human contribution to the global mean temperature increase over the period 1951 to 2010 is 1.1 to 1.4 degrees Fahrenheit," end of the quote. Again, the word likely is taken from the IPCC calibrated language, meaning that there is a 2/3 chance that the true human influence lies within this range. Now, the observed warming over this period is 1.2 degrees Fahrenheit. Hence, the key finding goes on to state that there is, quote, "a likely contribution of 93 to 123% of the observed 1951 to 2010 change." Because this best estimate lies near the center of that range, it is appropriate for me to stand here and state that this report defends the statement that human activities have caused all of the observed warming since 1951 in the context of this quantified uncertainty. This is a strong statement, but I think one that needs to be made. These statements in the report about the lower bound and the best estimate of the human influence on climate are supported by a vast body of peer-reviewed scientific literature spanning several decades. The lower bound is particularly constrained by our understanding of the climate system. However, the report does not make a statement about the less well-constrained upper bound. This worst-case scenario is important in a risk assessment context and is perhaps the topic of future national climate assessments. I reiterate that I do not speak for government policy or positions. However, I will say that there is little doubt that human actions, principally the increase in atmospheric carbon dioxide from burning coal, oil, and natural gas, are responsible for most, if not all, of the observed warming to date. There are no credible alternative explanations. Thank you.
Thanks, Michael. Our final speed talk is Ben DeAngelo, who will be giving us some perspectives on climate change mitigation.
Thank you. I'm Ben DeAngelo, Deputy Director of the Climate Program Office at NOAA. Last talk, hope you're still with us. This chapter, it's chapter 14, informs important mitigation questions. It includes analyses of Paris and includes a primer on geoengineering, so the non-controversial things. We wanted a chapter like this in the report to be policy relevant, but without being policy prescriptive. So this chapter stays in the science lane. I'm okay with the space bar. Okay. Reducing net emissions of CO2 is necessary to limit long-term warming. CO2 is dominant and persistent over the long term. IPCC estimated 15 to 40% of CO2 emitted between the present and end of century will remain in the atmosphere longer than 1,000 years. The persistence of warming associated with CO2 emissions is longer than the atmospheric lifetime of CO2. Other greenhouse gases like methane and black carbon aerosols exert stronger warming effects than CO2 on a per ton basis, but they do not persist as long in the atmosphere. Therefore, mitigation of non-CO2 contributes substantially to near-term cooling benefits, but cannot be relied upon for ultimate stabilization goals. In the near term, temperature projections are still strongly dominated by natural variability, the Earth system response to past and current greenhouse gas emissions, and by model dependence. Long-term temperature projections, however, after mid-century, show that choice of emissions pathway is the dominant source of future uncertainty. Don showed a figure earlier illustrating the point. Stabilizing global mean temperature to less than 2°C requires substantial reductions in net CO2 prior to 2040 and likely requires net emissions to become zero or negative later in the century. Because stabilizing global temperature requires net CO2 emissions to approach zero for a 2°C or any desired warming objective, an estimated range of cumulative CO2 emissions commensurate with that objective from the current period onward can be estimated. Cumulative CO2 emissions must stay below about 800 gigatons of carbon in order to provide a 2/3 likelihood, a good chance, not a guarantee, of preventing 2°C of warming above pre-industrial. A robust feature of model simulations is a nearly linear relationship between cumulative CO2 and global mean temperature. This facilitates estimation of compatible cumulative carbon emissions associated with different levels of future warming. Key sources of uncertainty for compatible so-called carbon budgets include climate sensitivity, the response of the carbon cycle including feedbacks, the amount of past CO2 emissions, and the influence of past and future non-CO2 species. Increasing the probability that any given temperature goal will be reached implies tighter constraints on cumulative CO2, and relatedly, higher emissions in the near term imply the need for steeper reductions in the long term. We estimate illustrative dates when cumulative carbon emissions reach amounts commensurate with 2C and 1.5C above, pre-industrial. Between 1870 and 2015, human activities emitted about 560 gigatons of carbon. This means for 2C, approximately 230 gigatons of carbon more CO2 could be emitted globally. If one assumes future emissions follow RCP 4.5, one of the scenarios used throughout our report, this cumulative carbon threshold is exceeded by around 2037, while under the higher emission scenario, RCP 8.5, this occurs around 2033. To limit warming to 1.5C, the estimated cumulative CO2 budget is about 590 gigatons of carbon, meaning only about 30 gigatons of carbon more of CO, in the form of CO2 could be emitted. And this would occur in the next few years. So the idea of a 2C goal can be found in the literature actually as early as 1975. There's an interesting paper and presentation by Nordhaus that we mentioned in our report. Since that time, the concept of a 2C goal gained attention, obviously, and is now formalized in the Paris Agreement. We did make changes in our report to reflect the U.S. announcement on Paris, but given the timing, there was no literature to assess in our report about the implications of that announcement. We do highlight this very good work of Fawcett et al. Under a scenario in which countries maintain the same pace of decarbonization past 2030 as they announced in their first actions, the INDCs, leading up to 2025 or 2030, there is some likelihood, less than 10%, of preventing 2C relative to pre-industrial. This scenario, I'm talking about the middle, that kind of flat line there, this scenario thus holds open the possibility of achieving this goal, whereas there would be virtually no chance if emissions climbed to levels well above those implied by country announcements. Greater emission reductions past 2030 increase the likelihood of limiting warming to 2C or lower to about 30% and almost eliminate the likelihood of an increase greater than 4C or 7 degrees Fahrenheit. Our last finding touches on climate intervention and geoengineering. Again, like I said, what we provide is essentially a primer on this topic. We state further assessments of the technical feasibilities, costs, risks, co-benefits, and governance challenges of climate intervention or geoengineering strategies, which are as yet unproven at scale, are a necessary step before judgments about the benefits and risks of these approaches can be made with high confidence. I'll end there. Thank you.
Okay, thank you, panelists. So we're on schedule. We have most of an hour left to entertain questions from the floor to the panel members. There's a microphone here in front, so please consider offering a question. Yes.
Hello, I'm Mike McFadden from NOAA. First, I want to congratulate Don and all the authors of this report. It's really a superb assessment of the present state of the science on climate change and its impacts over the U.S. I've used the material myself in giving public presentations, and it's been very well received, in fact. I mean, the graphics are clear, and it helps make the story easy to tell. So my question is for Don. You started out, the first words you said were, "We got it out." And for that, we're all very happy. We were holding our breath there for a while. But getting it out is just the beginning of the story. So what's the happy ending to this story? I mean, what is it that you would like the impact of this report to be, and what steps are being taken to achieve that?
Good question. So we were so concerned about getting it out that we have not planned any special events for the future, but I think that's more likely to happen as the second volume gets completed, and we look at this as the big picture of not only the science of climate change, but then the potential impacts on the American people, and looking at that as an entirety, I think that we're going to need to do some kind of special events that relate to that. We don't have, other than presenting the science and the understanding of it at a series of different meetings like this one, we don't have any particular plans at this point for special activities with CSSR. But it is important that we try to keep this in the public's mind. There will be a special EOS, there was already an EOS article that I and my co-coordinating lead authors wrote that has appeared online. It will appear in EOS published next month, and so in January. And I think we need to do some more things, but we haven't really planned anything that I'm aware of. You want to?
Go ahead.
No, thank you. Yeah.
Dr. Wilson.
David, thank you. I teach this stuff. Class starts in a month. Your timely report is very important to me. I find it compelling to compare the total anthropogenic forcing with the net energy gain of the climate system as shown by GRACE and by the accumulated energy in the oceans and in the surface and in the atmosphere. What caveats should I offer my students with regard to the claim that we have several times the cause needed in the anthropogenic forcings to explain the effects observed in the accumulation of energy in the climate system?
Bob, did you want to go talk to that first? Bob, in terms of the ocean heat content?
I think it's a broader question on sort of the energy balance of the planet, but in terms of the ocean heat content, I think a major caveat is we don't have complete measures of ocean heat content. We only have them down to 2 kilometers, as you show in that figure. Translation of GRACE into heat is a couple steps removed. If by GRACE you're talking about changes in ice mass. But I think in terms of the broader energy balance question, I think we would turn to some of the other people on the panel.
But certainly, in terms of the overall forcing, there was a paper a couple years ago, and I can't remember who the lead author was now, that looks at it's kind of the first absolute proof that satellite and other data sets show that the forcing on the climate is matched by the changes in the energy system that we would expect, and particularly for the changes in CO2. We're really starting to tie all those loose elements together that show that the system is operating the way we think it. We have thought it was in the first place, but it's really kind of coming together. I don't know if that handles what you wanted or not, but.
Are you referring to the paper by Feldman?
Feldman, yeah.
I would add that, not so much a caveat, but, increasing our confidence is that the radiative properties of gases like water vapor and CO2 and oxygen and nitrogen have been well known since the 19th century. This is not rocket science. It's steam engine science.
So thank you, Dr. Wilson. It's good to hear that you're taking this to the younger generation. Other questions?
What was the rationale for using 4.5 as the lower bound when the Paris Accord goal was quite a bit lower than that?
No, we didn't. We actually used RCP 2.6 as the lowest scenario, which is more or less matches the goal of Paris, which is trying to get to 2 degrees. We did not have a scenario or any model runs that went below that, so we could not really talk much about the 1.5 degree aim of Paris. But RCP 2.6 was a key scenario in many of the analysis, and we did show results in the report relating to that. Go ahead.
Just to add one thing to that, for consistency and cohesiveness between this volume and volume 2, the rest of the National Climate Assessment, a decision was made very early on in the process for communication and simplicity to focus not exclusively, but most heavily on RCP 4.5 and 8.5. Again, to have that more greater consistency between the underlying science in this report and the impacts and risks stuff in Volume 2 of the National Climate Assessment.
Okay, please.
Hi, thank you all on the panel.
We can't really see you, so if you could just give your name and...
Oh, Kathy Durbin.
Thanks, Kathy.
This may not be a fair question to ask, but I'm going to ask it anyway. So in 2013, the National Research Council did a special study on abrupt impacts of climate change. And since a number of your chapters seem to have been touching the kind of boundaries of some of the existing projections with moving into that realm, I just wonder if any of you would comment on whether we need to revisit that report.
Is this? Yeah, I didn't fully understand that. You were talking about rapid changes? Or?
Yes, in 2013, the National Research Council came out with a report called Abrupt Impacts of Climate Change, which kind of said we're okay till 2050, and then we'll have to keep studying. But some of your chapters actually approach kind of tipping points. I mean, on the Arctic, in the oceans, in extreme weather events, and temperature increases. So
I think we raised the possibility that such abrupt changes could occur sooner, that, particularly in terms of potential impacts that are not really discussed much in this report, where you get effects on food systems that then you get feedbacks into the climate system from changes in land use, et cetera, that result. That is not touched on much in this report, but I think in the overall assessment will be looked at more. Anybody else?
Yeah, so I mean, when we think about in the context of tipping points, I would distinguish between abrupt change and an abrupt commitment to change. Because, for example, if we think about marine ice sheet instability in the Antarctic, since that 2013 report, there's evidence that marine ice sheet instability is active in parts of the Amundsen Sea embayment. And so we may have already passed a tipping point with respect to, say, Thwaites Glacier. That doesn't mean that there's going to be an abrupt change in sea level, which is, I think, one of the fuzzy concepts when we start thinking about tipping point, because the idea of abrupt change and abrupt commitment to change sort of get mixed together. We didn't find in the discussion of tipping points any particular tipping points that jumped out as having the potential to cause abrupt change within, say, the next few decades. But certainly there are critical thresholds that could be passed in that time period.
Thanks.
Hi, Bruce Willicke from NASA Langley. Since the observations are critical to us over a long time period in understanding climate change, and we now have a much better idea of sort of the known unknowns, was there any attempt in this report to talk about perhaps the world designing a climate-specific observing system as opposed to sort of the hodgepodge of weather and research and other things we have now, or just do the best with what we have in the future?
We were told to specifically not go into what additional research should be done, but to more focus on the assessment process. There is a separate paper that just came out recently was accepted, I guess, in Earth's Future, that does look at the question of observing systems that several of us are co-authors of.
Right. Is there any interest in the future in the USGCRP doing anything on that in a broader, integrated way?
I think there's certainly a lot of interest within USGCRP discussions between the different agencies relating to that, but that was beyond the scope of this report.
Okay, thanks.
Hello, Zeke Housefather from Berkeley Earth. Somewhat specific question, but in Chapter 6, there's a fair amount of discussion of changes in extremes on a daily basis around extreme heat events, particularly showing much larger concentration of extreme heat events in the 1930s than presently today. However, all of that is based on raw daily temperature records as compared to the homogenized monthly data that's used for many of the other climate records. And I'm curious why there wasn't a bit more caveats around the challenges in using such daily data, associated with time of observation changes, station moves, and the rest that make it difficult to interpret those sort of records.
Yeah, so I'll let Dave deal with that primarily, but there were limitations. This report already ended up much longer than we intended it to be, and so we were trying not to go too much into the discussion of the records themselves in this report, figuring that was covered in other papers, but certainly we were well aware of those issues.
Yeah, I'm not sure I have a whole lot to add to that, but
I think it's on.
It's on.
Oh, okay, yeah. I mean, the 1930s are certainly the sort of the warm period of record in terms of high temperatures, but not necessarily low temperatures. So you see a lot of the warming in the U.S. was driven by winter temperatures, and you see it in changes in the cold spells. You had a very sort of almost linear decrease in cold spells, but you had the big spike in warm spells in the 1930s. So, it's very useful to kind of break that apart, looking at the daytime highs and the nighttime lows.
Thomas Stalker from the University of Bern. First of all, congratulations to this great report. I wish many more countries would have such a comprehensive national assessment. I think that would bring down the message from IPCC right into the countries where ultimately decisions have to be made. I'm also delighted to see that you took as a firm basis our fifth assessment report. Even after 4 years, this is good news. Even some of the formulations are very similar to what we chose in AR5. I do have a question regarding the geoengineering. I think it's very good that you had a chapter on geoengineering. If I understood correctly from your presentation, it's more on the global scale aspects of geoengineering, but I think there is a huge potential also to say scientific things about what it means for your country. If geoengineering or of any type were to be deployed, I think it's important that that topic is also covered in Volume 2. Maybe you want to comment on that. Thank you very much.
Okay. Yeah, thank you. I think it's a good point, a very good question. One thing I didn't mention, and I don't believe we mentioned in our report, is that a couple years ago, or less than 2 years ago, the U.S. Global Change Research Program came out with a revised strategic plan. And in there, it was the first time that we included some language about geoengineering and climate intervention. And that was really our kind of first, I would say, conservative, tentative step towards talking about the subject, because it's always been difficult to even have a conversation about it. And I say that because the strategic plan does kind of opens the door to the agencies having at least a discussion about a U.S.-focused discussion or program. There isn't, I would say, there's still nothing formal moving in that area, but I think that strategic plan and this report, I think at a minimum has opened up the door a bit more to having the conversation.
Dave, did you want to add to it?
Yeah, so thank you, Thomas. Yeah, we're gently kind of moving into this area, and right now in the U.S. you don't really have a center for geoengineering research. But as we point out in this chapter, we think that we have to raise that issue because when you look at the scenarios, you're left not feeling like we don't have the confidence that we might like to have to stay at a lower temperature. So geoengineering is somewhat immature in the world, and so we kind of set the stage for asking for more maturity, so to speak, in the future in light of these scenarios, of the reality of these scenarios.
I don't want to leave you with the impression that I'm a geoengineering aficionado. I think to avoid geoengineering, I think it's really important that at an early stage, the statements are very clear about the risks, and I saw that, about the dangers, and about the unintended side effects. All these things we try to encapsulate in one paragraph, even at the level of the summary for policymakers, where every country had to take note of. So I think it's really very important at this point in time, where I sense a rising enthusiasm in some circles for interventions of that kind, and yet we don't really know. Just this morning in a lecture I learned that the stratospheric warming associated with aerosol injection into the lower stratosphere is in the two-digit range of 50 to 60 degrees Celsius with the volumes of sulfate being injected. I don't know whether that's a robust result, but these are the interesting things I think the public needs to know.
You know, this is the problem, and part of the, as you're alluding to, we just don't know enough at this point to be very conclusive about our statements. I think we did try to expand upon what was in the IPCC assessment, but we also felt it was premature to go very far without a lot more research, and that's obviously what is needed.
Thank you.
Well, and I think you could conclude that we're approaching a threshold where we perhaps need an international assessment to really clarify the landscape of possibility and impact. So, because as we've seen in the past, one country's opinion doesn't necessarily carry as far as you might like. So, and Thomas, as long as you intervene, thank you for your question, and thank you for a wonderful Working Group 1 report. In some sense, we stood on the shoulder of giants, or at least those who came before us, and really made what I would say is excellent use of the Working Group 1 AR5 as a starting point. So that made our job a lot easier. I also point to this slide here that's pointing to the US GCRP website for this report. We really had an excellent technical support unit, TSU, for this report, based at the National Center for Environmental Information in Asheville, North Carolina, as well as the GCRP office in Washington. And so I urge you to go there. It's very interactive and easy to browse and easy to grab onto whatever part of the report you want.
One thing I might add, since I skipped over one of my slides, was the 32 lead authors that was mentioned earlier, but the 19 contributing authors has not been mentioned today. And we really did appreciate the efforts of those who, when we had a question, we would reach out to others and got input and made those people contributing authors. And they were very, very helpful to us. The other thing, Dave mentioned that we went through 7 reviews as part of the process. That included the public review, a special review by the National Academy of Sciences, and numerous reviews, both with the steering committee and with which is comprised of different members of the agencies, plus multiple reviews by the agencies themselves, the US GCRP agencies. So we got a lot of input, none of which changed the basic nature of the report, but certainly did add to the report and helped us to expand the discussion in some areas, particularly in oceans. I think we expanded greatly over what we had initially. That really made it a better report. So we really appreciate all that extensive amount of input we got from all those many, many different people that did send in review comments.
So we have a shrinking population here. Do we have some more questions from the floor? Comments from the panel that they didn't get a chance to make?
Well, we would appreciate input from you all as to where we should go from here. I think this question of what further reaching out should be done by USGCRP and by the community of scientists involved in this is something we're all interested in, but we need that input.
I think as a U.S. citizen, you can be pleased with how well the process worked. Don Webels, our champion here, was actually in the White House as helping the previous president's science advisor on climate matters, and that's when this report started, and then it carried over into the new administration. But the GCRP process is really nicely structured, and it's a bit of a well-oiled machine now in terms of how it gets the agencies on board in a cooperative way to produce something of this complexity that takes 2 years of gestation to make. So, and as like Don says, and Mike Kuperberg would say if he were here, what else do we need to do? What's next? There's people waiting to be tasked, as well as the scientific community where you see this wisdom of crowds really work. So I guess we're close to closing if we have a silent group here. Any other questions that people would like to ask? Yes. And this event is being recorded by AGU, and I believe it'll be available on their website to review or to show others.
Thank you very much. I want to thank everybody. I'm curious, how much is being discussed by your group to communicate this to the public rather than maybe making it available through K through 12 education levels or making an impact outside of the scientific community? The other issue is unfortunately global climate change has become a political issue. And how much is that brought into I mean, you've done a fantastic analysis, but now where does it go, as the committee, where do you guys take it to get it to the public? Not just to the scientists and to the community,
Well, it's not just for the scientists by any means. It is part of what we're reporting to Congress. So this is going directly to Congress, to every member of Congress, as input on the understanding of the science. But we don't have special activities planned for how this is then taken into the classroom or at different levels of education. That's just not part of the purview of what's being done with this at this point. That doesn't mean we shouldn't put some emphasis on that, but
do you have any thoughts on how you can start to communicate it out? I mean, as the committee that's just wrapped up this important work, have you been discussing it in sidebar conversations or anything, or is it just not?
I think we put so much energy into getting it out that I don't think we've gotten to that point yet. There certainly is talk within USGCRP as to how you approach, how you use this kind of information in STEM education process, et cetera. It just hasn't been a lot of activities in that direction yet, but that should be developing.
So does that have to be a change in your mandate or your directions to get that?
Our mandate as a group of scientists was to write this report and to get it to Congress, get it approved and get it to Congress. The steps beyond that are really up to the community and to the U.S. Global Change Research Program and the agencies there, that are involved in that. Anyone else want to add to this?
I was actually pleasantly surprised how organic this process actually is. I gave a lecture last week to a group of park rangers, and the speaker before me had more figures from the National Climate Assessment than I did. So it gets out there. So I suspect that the only thing we can say right now is we're putting the ball back in your court, and please utilize this in any way you see fit for whatever outreach to the public you do, whether it be in your classrooms or in public lectures or talking to park rangers.
Yeah, and I think that is a good point. Everybody and several people did comment on how they're using it in their classrooms, and this is monumental work that is put into a lot of different avenues. So I want to acknowledge you guys did a great job. Thank you very much. And so I don't mean to discredit your hard work, and I realize, you know, getting in front of Congress is, you know, a challenge in itself, but where do we go? I guess my question is where does the committee go now? And is that something?
Well, I think we've fulfilled our charge for this. We are some of us are working on the second volume as well, because there will be a summary of this that goes in the second volume, and we're also interacting with the other chapters that are looking at the impacts on various aspects of society and different segments. So that work continues. But the main job of the committee was to write this report and get it out there.
The rest of us go back to our day jobs.
But, I mean, I'll add to that you bring up a good point, that you would want this report to have impact rather than just collecting dust on a shelf. And I think we kind of split the difference, that it isn't our mandate to be the communication arm. On the other hand, we want to meet the communication arm halfway. And so this executive summary that's being passed out at the back took a tremendous amount of effort in terms of effort per page, effort per word to create, where the objective was different. It was to communicate beyond the scientists, as well as maintaining a scientific rigor. So, you know, IPCC has done this with its summary for policymakers, et cetera, that the system, if you'll have it in the world, knows that these 500-page scientific reports don't penetrate to the audience who you would like to have the main message. And so it really has to be distilled out separately. And so we went so far as to print separate booklet. Well, first of all, to make it and have it be positively kind of draw people in with boxes and graphs that are understandable, and then to explain the report in the front so you knew what the credibility factor was, and then put a shiny cover on it and make a lot of them. And when you go to that website, you can take the executive summary booklet separately. And so we've created the tool with the thought that the people that you're thinking about would be able to get this. But we kind of stop there. It's this common but differentiated responsibilities.
Yeah, one comment I might make, though, is many of us as individuals are certainly doing a lot of reaching out, but that's not defined as part of our duties in writing this report.
So if I could make another comment. So one of the challenges in doing these sort of very regular, so the law says every 4 years we should put this out. And one of the challenges is to come up with a new way of presenting material, so it's not simply a rehash of the one that was done 4 years and the 4 years before that. One of the things we're trying to do with the Volume 2 is, and I mentioned it in my talk about extremes, is what we call risk-based framing. And that's begin to bring in some of the elements that have some of the higher risk, like very high temperatures, high heat waves, and things like that, and the risks that they pose, and bring that into some of the areas like agriculture or energy and things like that. So that's sort of a next step. What goes beyond that really is to be determined, but you know, I look at these assessments as really should be evolving somewhat, as opposed to being very similar to the previous one that was similar to the previous one.
Okay. Thank you.
All right, thank you.
Katie?
And if I might just say something. My name is Katie Reeves. I am the Engagement and Communications Lead for the USGCRP.
Can you hold the microphone closer?
Oh, I'm sorry, I'm short, so it's difficult. My name is Katie Reeves. I'm the Engagement and Communications Lead for the U.S. Global Change Research Program's National Coordination Office in D.C. One of the things that we do have that came about with the third National Climate Assessment is a group called NCANet, which is a network of networks. These are people who choose to join calls on a bi-monthly basis. They're people who are working with climate change in some way. And they are essentially working together to spread the word about the U.S. Global Change Research Program and its work, primarily the National Climate Assessment, the Climate Science Special Report. So, you can come and talk to me. We can get you signed up for that, so you're on the mailing list at least. Other things that have happened, and I believe, Bob, you were on the Reddit AMA, correct? Right, so there are activities that are going on around this to make sure that the people who need to hear about this are hearing about it. But please don't hesitate to come and talk to me. I am here at the back of the hall, and I am in the exhibit hall, booth number 745. So please, if you have thoughts, if you have suggestions, I am all ears.
Thank you, Katie.
Thanks, Katie.
Final questions?
Okay.
So if any final comments? So if not, I think we should give our presenters another round of applause.
Thank you all for being here. It's the community, the science community that makes all this happen and will help get the right message to the American people.
Thank you, everybody.